So today we are going to discuss the derivation of the Ohm's law, or you can say the Ohm's law in a microscopic form. Okay. So what's the statement of the Ohm's law? So consider a conductor whose area is cross-sectional area is A, length is L, and it is applied to a V potential difference. Okay. Now, as you know, when a conductor is applied to some potential difference, there is generation of electric field, and that electric field apply a force on a charged particles, or you can say free electrons, due to which the electron constitute a current. Now, according to Ohm's law, the potential difference applied across the conductor is directly proportional to the current flowing in the conductor. Means this is the basic law. Okay, this is a basic statement of the Ohm's law, that potential difference is directly proportional to the current flowing through a conductor. Okay, now we have to develop a relationship. So in the previous video we have seen that the relationship between the electric current and the drift velocity, okay, which I have written I equal to N E A V D, where N is the number density, number of electron per unit volume, E is the charge on electron, A is the area, cross sectional area, and V D is the drift velocity. Okay, now what VD is also equal to, that we have discussed, okay, in the previous video, that VD is equal to E upon E, this magnitude, E into E tau upon M. Okay, so we have to substitute the value of ED, which tau is the relaxation time. Okay, substitute the value of VD in our equation number. Suppose I can say this is the equation number 1. So we have to substitute the value of VD in the equation number 1. So we are getting this result. Okay, so I simplify it and I am getting Ne square A E into tau upon M. Now here we have introduced the various parameters. Now we can also know that the electric field applied to a electric field of a conductor and the relationship between the potential difference. We have learned it. So what is in the chapter number 2, the relationship between the electric field and the potential. Okay, electric potential. So which is given by E equal to V upon L. So we can replace this E in terms of potential difference and length. So I have written down, I replace the E with this value. Okay, so in place of E, the V upon L has come. Okay, now after that we perform a cross multiplication. Okay, so we perform a cross multiplication of this term. So I into ml upon Ne square A into tau. Okay, now V equal to IR, or we can say, now compare this equation, V equal to IR and V equal to ml Ne square A tau into I. So if you compare this equation with this, okay, or if you are going to compare, so suppose I written as R into I. So if you are going to compare this equation, F V equal to Ri or V equal to ml Ne square A tau into I, you will find that resistance, the value of resistance is equal to ml of this constant, because this whole value is a constant value. Why? Because the mass of the electron is not going to be changed, the number density we assume it is a constant for this case, the relaxation time is constant. If the temperature and certain things are not changes, then definitely the relaxation time is constant. The geometry of a conductor is constant. So we can say that this whole parameter is a constant. This whole parameter is a constant because it contains values, the things which are constant in nature. Okay, in the upcoming videos we learned that how the limitation of the Ohm's law, but here we assume a standard situation in which these parameter, mass, length, area, relaxation time, charge and number density, these are, if they are constant, then we can say that V is proportional to the I. Okay, V is proportional to I. The potential difference across the conductor is directly proportional to the current flowing in the conductor. Now Ohm's law, as I said earlier, that we discussed the Ohm's law in the microscopic form. That microscopic, we introduce a microscopic variable. Okay, or you can say microscopic terms. You know, this is the mass of the electron, charge of the electron, number density. Okay, so now one more thing you can see, that resistance equal to, okay, so we can also develop a relationship between the resistance and resistivity here. Okay, so I need to rough this here. Now what we know from our previous lecture discussion, resistance equal to rho L upon A. Okay, that is the SI unit of the resistance, or you can say that is the formula for resistance. Now if you compare this value, those two equations, R equal to ml upon ne square tau into A. So more precisely I am writing here L upon A. Now if you compare R equal to rho L upon A and R equal to this constant into L upon A, you will find that this rho is equal to this constant. Okay, so we can find that this resistivity is equal to m upon ne square tau. So we have developed our relationship for the resistance, and from the resistance we can get the relationship for the resistivity in terms of the microscopic terms of the charge. Okay, now so this is the simple derivation. Okay, first you have to know the current. Okay, so it is basically these are the chains. Okay, for that you have to know what is the relationship between the current and the drift velocity, and then you have to substitute the value. After substitution you will get this result. Okay, so these are particular the derivation of the Ohm's law.